should know the voltage, the current, and the resistance and the resistivity. These symbols show the resistor and the ground, the symbol of the battery connection, and the rectifier. This is the symbol of the switch and the diode. The most common and the famous law in cathodic protection we apply every day is Ohm's law. We should know also Kirchhoff's law. Kirchhoff has two laws, voltage law and current law. The voltage law states that the sum of the sources voltage around any closed loop of a circuit is equal to the sum of the voltage drops across the resistance in that loop. As shown, the sum of the voltage sources is 24 volt in here and here, and if the current is 1 ampere in this circuit, the voltage drop in the first resistance is 8 volts, and the second resistance 8 volts, and the third 8 volts. So the total voltage drop is 24, equal to the sum of the sources. For the current law, as much current flows away from a point as flows toward it. We will use this in the parallel circuits and in tracing current flow in complex piping network. 6 ampere inlet and also 6 ampere output. In the series circuit, the current is the sum everywhere, is the same. No change in current in the series circuit. The voltage drops may all be different depending on the value of each resistance. Each resistance have its own voltage drop, but the sum of all the voltage drops will equal to the source, the voltage source, or the sum of the voltage sources, like Kirchhoff's voltage law. The total resistance can be added and give the sum of the individual resistances. This shows the series resistor circuit. We can calculate we can see that the current is the same through all the resistance. The resistance can be calculated R1 plus R2 plus R3 to give the total resistance. In the parallel circuit, voltage drop across each branch is the same and is equal to source voltage. So in the parallel circuit, the voltage is constant, but in the series circuit, the current was constant. In the parallel circuit, the total current flowing into and out of the junction point of the branches equal to the sum of branches currents. That's Kirchhoff's current law. The total resistance is equal to the reciprocal of the sum of the reciprocals of the individual resistance. So the total resistance is always less than the smallest resistance in the circuit. This shows a parallel circuit. The current can be calculated or can be added together to give the total current. The resistance, the total resistance can be calculated from this formula. For basic chemistry, we should know the difference between elements and atoms and ions, compounds, and know the acidity and alkalinity. Oxidation is a loss of one or more electrons from an atom or molecule, which then form a positively charged ion. Reduction is the gain of one or more electrons to an atom or molecule, which is then form a negatively charged ion or neutral element. This shows the oxidation of the iron. The iron atom could be oxidized to form ferrous ion plus 2 electrons or ferric ion plus 3 electrons. Also at the cathode, the oxidation reaction happens and hydrogen ions will gain electron to form hydrogen atom. Then two hydrogen atoms combine together to form hydrogen molecule. This show a corrosion cell which consists of the anode and the cathode and the metallic path and the electrolyte. Here we can see the anions, which is the negative ions, go toward the anode, which is the positive electrode, and the cations, which are the positive ions, go toward the cathode, which is the negative electrode. At the anode surface, oxidation happens, and the electrons which come from oxidation reaction will move in the metallic path from the anode to the cathode. And the positive ions will move to the cathode inside the electrolyte. We should know the conventional current flow, which in this direction, the conventional current flow is from the anode to the cathode inside the electrolyte, and from the cathode to the anode in the external circuit or in the metallic path. The anode reaction is oxidation of the metal to a metal ion plus electrons. N is the number of electrons involved, so we can see the iron atom can be oxidized to iron ion plus electrons. Aluminum also can be oxidized to aluminum ions plus 3 electrons. At the cathode, the reduction reactions happen. If we talk about neutral environment, 2 molecules of water plus 1 molecule of oxygen plus 4 electrons will give 4 hydroxide ions. In acidic environment, the hydrogen ion will be reduced to the hydrogen atom. This gives us the energy to convert ore to metal. It's clear that the potassium and magnesium require the most energy to convert from the ore phase to the metal phase. Also, the gold have the least energy required to convert from the ore to the metal. Potassium and magnesium are more active. Platinum and gold are more noble. This is a practical standard EMF series of metals, which shows that the gold has the more positive standard electrode potential. The magnesium has the more negative standard electrode potential. For practical, the galvanic series can be calculated or listed like this in seawater. If we have 2 metals in seawater, the more active one would become the anode, and the more noble one will become the cathode. As we see, magnesium has the more negative potential here, and the carbon or graphite has the more positive potential here. If we have a corrosion cell consists of steel and magnesium, the magnesium will become the anode and the steel will become the cathode. If we have another corrosion cell consists of steel and copper, the steel will become the anode and the copper will become the cathode. Nernst equation expresses the exact electromotive force of a cell in terms of the activities of the products and reactants of the cell. It demonstrates how the metal ion concentration in the electrolyte affects the potential of the electrode. As we see, the electrode potential in existing solution equals the standard state half cell electrode potential plus this formula. The universal gas constant multiplied in the absolute temperature. Here is the number of electrons transferred and Faraday's constant. Here is the activities of the metal ion in solution and the activity of pure metal. Faraday's law relates the weight loss of a metal in a corrosion cell with time and current. The weight of any material deposited on the cathode or liberated from the anode is directly proportional to the quantity of electrical charge passing through the circuit. This is the formula of Faraday's law. The weight loss equal the electrochemical equivalent multiplied by the current and time. An example, if we have a silicon chromium cast iron anode, which is designed to protect the structure for 40 years and has 1 ampere of current output, and we know that this anode or this type of anode has a consumption rate of 0.34 kilogram ampere year. So if we want to calculate how much kilograms, what's the weight of the anode which will protect the current for 40 years if 1 ampere is output of this anode, we can use this formula. We need 13.6 kilogram from silicon chromium cast iron. Reference electrode are used to measure the structure to electrolytic potential, which is a potential difference between the structure and the reference electrode in electrolyte. We should know the standard hydrogen electrode, which is a primary electrode and used to be the base of potential of other reference electrodes. The other reference electrodes which used in cathodic protection is copper-copper sulfate reference electrode, silver-silver chloride, and the calomel and zinc reference electrode. Here is the copper-copper sulfate, which is the most popular one. Copper-copper sulfate reference electrode consists of a connection for the test lead in the top, then a removal cap, the copper rod in the center, which immersed in a saturated copper sulfate solution, and it must be saturated. So here is an undissolved copper sulfate crystals. We should confirm that through the clear window. And here is a porous plug which will be in contact with the soil. We should pay attention to the polarity and the connection when take structure to electrolytic potential. If we connect the reference electrode to the positive terminal of the meter and the negative terminal of the meter to the pipeline, and the meter shows positive reading, what does that mean? That means that the meter displays positive, the reference electrode is positive with respect to the pipe. But if you connect the positive terminal of the meter to the pipeline and the negative terminal of the meter to the reference electrode, and the meter shows negative reading, this is the connection method we use in cathodic protection surveys. This means that the meter is negative, the pipe is negative with respect to the reference electrode, which is protected here. Reference electrode convergence, we must know how to convert the potential to another, from one reference electrode to another reference electrode. So we use these values to convert from one to another. Polarization. As we inject current to the metal surface, what happens? The polarization occurs at the anode and the cathode. Polarization is related to depletion of reactants and buildup of reaction products. The polarization behavior is opposite to the direction of the current or the corrosion current. Polarization lowers the potential between the anode and cathode, which is good for cathodic protection. Polarization increase. As the polarization increases, the current decrease. Also, the polarization stabilizes at corrosion current. We normally measure the mixed potential. Here is even diagram. In even diagram, it shows the anode open circuit potential, the cathode open circuit potential here, and the anode open circuit potential here. When we take measurement from the pipe surface to the structure to the electrolyte, what we measure is the mixed potential here. It is a value between the two anodic and cathodic sides. The cathode open circuit potential after polarization reach to this value, which is the polarized potential of the cathode. Here, the anode open circuit potential become to the polarized potential of the anode. These two curves shows the polarizations. Here, the polarization for the cathode, and here the polarization for the anode, with the red light. We can see that the difference between the two electrodes, the potential of the two electrodes decreases with polarization. Here, before polarization happened, there is a large difference between the anode and cathode. Here is small difference between the anode and cathode, and this is the value of the corrosion current. We have two main types of polarization, which are activation polarization and concentration polarization. The factors which affect polarization is or are the current, the anode to cathode ratio, temperature, electrolyte movement, electrolyte ion concentration. We will talk one by one. Current charge transfer. Since polarization is caused by current, then as the current increases, polarization increases. A greater current results in a high reaction rate, causing depletion of reactants and buildup of reaction products. Here is the effect of temperature on polarization. An increase in temperature caused to speed up chemical reactions which depolarize the electrodes. It's clear that with high temperature, here the red lines mean the high temperature, it's low polarization. Here, the orange lines is the lower temperature and the higher polarization. The effect of electrode movement as the velocity decrease, the polarization increase, and as the velocity increase, the polarization decrease. Here is the metal ion concentration. The polarization of the anode can be affected by the concentration of the corroding metal ion, which is a product of the metal oxidation. So, an increase in the metal ion concentration of the anode metal results in an increase in polarization of the anode and a decrease in the current. For oxygen concentration, we know that oxygen is a depolarizer. So, as the oxygen increase, the depolarization will decrease and the corrosion current will increase, and vice versa. The effect of pH on cathodic polarization. As the pH decrease and the electrolyte become more acidic, the polarization decrease and the corrosion current increase. And as the pH increase and the electrolyte become more alkaline, the polarization will increase and the corrosion current will decrease. Forms of corrosion, we have uniform or general corrosion, crevice corrosion, galvanic attack, bedding corrosion, intergranular attack, selective leaching. Also, the environmental cracking can be showed through corrosion fatigue or hydrogen embrittlement or stress corrosion cracking. What's the concept of cathodic protection? Corrosion is the result of an electrochemical reaction driven by a potential difference between anode and cathode, connected by an electronic path and immersed in the same electrolyte. In the case of uniform corrosion, a lot of microscopic anodic and cathodic sites exist on the surface of the metal structure. The concept of cathodic protection involves reducing the potential difference between the local anodic sides and cathodic sides to zero, resulting in zero corrosion current flow. By injecting current on the surface from an external electrode and polarizing the cathodic sides in an electronegative direction, we achieve the cathodic protection and reduce corrosion. What's the definition of cathodic protection? When the potential of all cathode sides reaches the open circuit potential of the most active anode side, corrosion on the structure is eliminated. This is the target of cathodic protection. Here, we can see a corrosion cell before applying cathodic protection on the left. Here is the anode, and here is the cathode. The corrosion current is 1 milliampere. We can see the potential of the anode side is negative 0.65 volts, and the potential of the cathode is negative 0.5 volts. When we apply cathodic protection, what happens? The cathodic protection will change the potential of the cathodic sides from negative 0.5 to negative 0.65. It becomes more electronegative. So both the cathodic sides and the anodic sides become cathodes. They have the same potential. So no need for corrosion current to flow from here to here. So the corrosion current becomes zero. It's reduced from 1 milliampere to 0 milliampere after applying cathodic protection. We can see the polarization of a structure on even diagram. Here, the cathode open circuit potential reaches the open circuit polarized, the polarized potential of the cathode. Cathodic protection will extend the polarization and increase the polarization of the cathode to reach the open circuit potential of the anode. And this value is the cathodic protection current. So the cathode polarized electronegatively from the E cathode open circuit to the E cathode polarized here and to the open circuit potential of the anode here. This image shows what happened in the anodic and cathodic sides when applying cathodic protection. For the first one, we have anodic sides with the color red, and the green positions is the cathodic sides. So the anodic sides always have the more negative potential than the cathodic sides. What happens when we apply cathodic protection current? The cathodic protection current will polarize the cathodic sides to potentials near the anodic sides. Here, for this corrosion cell, the anode size potential is negative 0.6 volt, and the potential of the cathode side is negative 0.5. When we apply cathodic protection, we will change the potential of these cathodic sides in the electronegative direction from negative 0.5 to negative 0.58. But still, there is potential difference. Here, the potential difference between the anode and the cathodic sides gets smaller, but still exists. In the third line, as the polarization continue, the potential of the cathodic sides shift again electronegatively to become minus 0.6. So it reaches the same potential of the adjacent side. As it becomes the same potential, have the same potential, there is no need for corrosion to happen, and the potential difference becomes 0, so no corrosion will happen here. Likely, these cathodic sides have potential of negative 0.6. As we apply cathodic protection, its potential electronegatively change it to negative 0.65. So also corrosion eliminated here. And the cathodic protection current continue to polarize the surface. All the surface will reach to the potential of the most active anodic sides here was negative 0.7 volts. So this is the target of cathodic protection, is to mitigate all corrosion in all sides of the structure. As the cathode polarized to the open circuit potential of the anode, here is a new anode of the cathodic protection anode. The cathode polarized to the open circuit potential of anode, resulting in 0 corrosion current. Here, the corrosion current was this value. After applying cathodic protection, and the cathode reached to the potential of the anode open circuit, So no need for corrosion to happen, and this value is the cathodic protection current which be applied. How to calculate the current requirement for cathodic protection? Depends upon the surface area to be protected. Also, the current requirement is directly proportional to the surface area. The protective coating reduce the exposed surface area, so it will reduce the current requirement for cathodic protection. The polarization behavior of the structure in its environment, the different type of environment will affect the polarization behavior and also the current requirement for cathodic protection. Current requirement is inversely proportional to polarization. The more the environment favors an increase in polarization, the lower the current requirement. Here is an example for current requirement calculation. If we have 12-inch steel pipeline with length of 1,524 meters, which was constructed in ASOIU, which has resistivity of 10,000 ohm centimeter. And we assume, the designer assumes that 10.76 milliampere per meter square will be sufficient for this bare surface area to achieve cathodic protection and satisfy the criteria. So we calculate the total surface area for this pipeline from this equation by dl. Surface area is 1,459 square meters, and the current requirement to protect this structure or this pipeline is 15.7 ampere. The cathodic protection criteria, as stated in NACE standard SB 0169, which is a control of external corrosion of underground or submerged metallic piping systems. This standard mentions several criteria for determining when adequate cathodic protection is achieved in section 6. Here is a structure to electrode potential of negative 850 millivolts or more negative, as measured with respect to a saturated copper sulfate reference electrode. This potential may be either a direct measurement of the polarized potential or a current applied potential. Interpretation of a current applied measurement requires consideration of the significance of voltage drops in the ears and metallic paths. Another criteria states that a minimum of 100 millivolts of cathodic polarization, either the formation or the decay of polarization, must be measured to satisfy this criteria. Here is the difference between the off potential or polarized potential, negative or minus the depolarized potential, must be 100 millivolts, or polarized potential subtracted from the corrosion potential. Here is the first criteria. The structure polarized to negative 850 millivolts according to copper sulfate reference electrode. We assume that this point, the anode circuit potential is this value. The second criteria assumes that the difference between the corrosion potential and the open circuit potential of the anode is 100 millivolts. When we measure polarization, how to measure the polarization on a structure. When we measure the structure to electrolyte potential and connect the negative terminal of the meter to the reference electrode and the positive terminal to the pipeline. Here we have the potential of negative 0.9 volts. This is the polarized potential. If this is an instant of potential, this is the polarized potential. In these measurements, we have a lot of voltage drops, which are clear in this curve or this image. Here is the resistance, the internal resistance of the meter. Also, there are resistance in the structure, in the longitudinal resistance of the pipeline itself here. Also, the connection from the electrolyte to the reference electrode here has a resistance which will be calculated in the circuit. This equation is the measured potential equals the true potential plus or minus the voltage drop in the electrolyte and the voltage drop in the structure, depending on the direction of the current. Another topic is the road and railroad casings. Casing to be electrically isolated from the carrier pipe. Carrier pipeline and casing may experience metallic short or electrolytic couple, or the ideal case is to be isolated. If short happens between casing and carrier pipe, metal-to-metal contact between the pipe and the casing. Typical causes of electropositive potential change along pipe at pair casing. The short results in electrical shielding of a carrier pipe from cathodic protection system. The corrosion is possible in either immersed, wet, dry, or atmospheric zone. Here is example of a short. This is the surface of the pipe, and this is the surface of the casing. This is a section. This section. This is a pipe and the casing outside. We take this section and enlarge it to know what happened. The pipe surface and the casing surface. Here may be electrolyte or maybe no electrolyte. If short happen, it's like we connect a wire between the surface of the pipe and the surface of the casing. This is the direction of the cathodic protection current from the soil to the casing. The cathodic protection current will be picked up by the casing surface, and then the current has two options. If electrolyte exists here, the current will discharge from the casing to the electrolyte, then picked up to the pipe surface. The other option, which is more easy, is to go in this direction through the metallic contact to the pipeline. Most current will go via this contact, and very less current will move in that direction. This situation is not acceptable and should be mitigated, because no cathodic protection current will reach to the pipe. The pipe is considered to be shielded from cathodic protection system. Also, the casing adds to current requirement of the cathodic protection system. This casing, which always be bare steel, will be added to the protected structure of the system. The other thing which may be happen is the electrolytic couple. If water or mud exists in the annular space between the pipe and the casing, the electrolytic couple actually between the pipe and air through casing, water, and mud, it may be exposed to atmospheric with dry zones. The electrolytic couple will allow the cathodic protection to immerse carrier pipe through the casing. Corrosion possible in areas of atmospheric or wet, dry, and under seals of spacers. Here is the carrier pipe and the casing. If we take this section and we confirm that the annular space contain water or mud. So this is the cathodic protection current will picked up to the casing surface, then will be discharged from here to the electrolyte, and then picked up again to the surface of the pipeline. So the pipeline will be protected. Casing current pickup and discharge has no effect on the cathodic protection of the pipe. So the pipe will receive all intended cathodic protection current from its source. So this electrolytic couple is an acceptable condition. How to indicate the problem? Electropositive potential change along the pipe near casing, or deterioration of protection in general area. If we found the pipeline potential and the casing potential are similar, we may expect short. Here, the pipe to soil potential survey. This is a pipeline and the casing is installed below the road. This is a ground bed. As we take structure to electrolyte potential from here to here, we can show that the potential become more electropositive as we come closer to the casing. Here, at the position of the casing, the structure become more electropositive. It become less negative than 0.8. So the carrier pipe in this area is not protected, which will cause corrosion to the carrier pipe inside the casing. The tests to locate the shorts are the structure to electrolyte potential survey, also interrupted structure to electrolyte potential survey. We can also do measure the resistance between the casing and the pipe. If the resistance is very small value, it will give indication for short between the pipeline and the casing. If we have high value of resistance, this may indicate isolated situation. Also, we can make voltage or ion drop method or casing depolarization test. Some pipeline survey methods include closed interval potential survey or direct current voltage gradient, alternating current voltage gradient, current mapping, and inline inspection. Here is a closed interval potential survey. We can measure the potential every step every 2 meter or 3 meter, we can measure the potential along the pipeline. Here is the technician gets the reading above the pipeline. He walk and get all reading for all positions here. Then these readings will be collected on a graph to determine the cathodic protection of the structure, like this. If we want to make analysis for these readings, the green readings are the on potentials, the red are the off potentials, the black readings are the depolarized potentials, and this dotted line is the criteria of negative 850 copper sulfate reference electrode. So it's clear when we compare the off potential to the criteria, we found areas which below the criteria, like this, and here, and all this area are below the criteria. So according or after doing the closed interval potential survey, we can identify the position which can satisfy the criteria of cathodic protection and then apply mitigation for these areas. The surface tests for coating evaluation like ACVG, DCVG, pipeline current mapper, hybrid, and coating resistance surveys. The potential gradient, in which we can calculate the gradient from earth current, the measured between two reference electrodes, like this image, current increase at coating holidays. Also, the gradients will increase. Here is the method of doing the DCVG survey to identify the location of the coating defect of the pipeline. The cathodic protection systems have two main types, the galvanic systems and embraced current systems. The galvanic system consists of anode and anode backfill, anode to structure connection and the structure. Here is the galvanic system. This is the structure and the anode. And there is metallic connection between the structure and the anode, the galvanic anode. The current direction here is from the anode to the structure through the soil, then from the structure to the anode in the metallic connection, like this. The types of galvanic anodes are magnesium, zinc, and aluminum. Applications of galvanic anodes: when we require small current and the lower resistivity electrolytes, when we need local cathodic protection systems to specific structure areas, we can use as a mitigation for stray current, or when applying cathodic protection in a congested areas. When we have shorted casing, we can use galvanic anodes to improve the potentials in this area. If we not intended for cathodic protection of pipe inside shielded areas or vessels interior surface, we use galvanic anodes. In the offshore structures, we use galvanic anodes. In the poorly coated or bare valves and fittings, we can use galvanic anodes. For embraced current cathodic protection system consists of anodes, anode backfill, and a power supply. The power supply is the difference between a galvanic and impressed current cathodic protection system. Here is impressed current cathodic protection system, which consists of the structure and the power source and the anode, and there is connection. The structure is connected to the negative of the power source, and the anode is connected to the positive of the power source. The current is injected here from the positive to the anode, then discharged from the anode surface to the soil and travel to reach all the surface of the structure, then picked up from the surface of the structure and travel here from inside the structure itself to this point, which called drain point, then collected in the drain point in the negative terminal to come back to the power source and close the circuit. So the positive terminal must always be connected to the anode. The application of impressed current systems, cathodic protection of underground or immersed structures, high current for bare, large, or poorly coated structures. If the electrolytic resistivity have a wide range, we can use impressed current cathodic protection. When replacement of cathodic protection for dissipated galvanic anodes, to overcome the stray current or cathodic protection interference problem. Also, for cathodically protected heat exchanger water boxes or oil heater treaters or other vessels, we can use impressed current systems. The interior of the water storage tanks and the exterior of above ground storage tanks, bottoms, primary and secondary, underground storage tanks and foundation piles and sheet fillings. The impressed current anodes have many types, include dimensionally stable, like MMO or mixed metal oxide and platinum. Another type is semi-soluble type, like high silicon chromium cast iron or carbon or conductive polymer. Another soluble type is iron. The most used is the metal oxide and high silicon chromium cast iron and the graphite. The power sources for cathodic protection in impressed current systems include rectifiers or solar cells, thermoelectric generators, and engine generator sets. According to the availability of AC current in the location of cathodic protection source or not. Here is a surface remote impressed current anode system, which consists of vertical anodes in a remote area connected to a positive header cable to the positive terminal of the rectifier, and the negative terminal of the rectifier is connected to the structure. Here is distributed impressed current anode system, but the anodes here are horizontal orientation. Also, the header cable connected to all anodes is connected to the positive terminal of the rectifier, and the negative terminal of the rectifier are connected to the structure. Here we can see the current, cathodic protection current with the yellow lines, which protect the structure. Here is a single anode in a close position to the structure. Current distribution from closed anode. The deep anode installation, if we detect a large structure. Here is the anode, are oriented in a vertical orientation. This is the active anode area here, and the anode surrounded with the anode backfill. Here is non-metallic casing. Also, all anodes are connected to this positive junction box to be able to measure the output of every anode. And the structure is connected to the negative terminal as usual. For the field measurements, we should know the different types of instruments used in cathodic protection surveys. We should know how to measure the structure to electrolyte potential, how to measure or use test coupons, how to do current measurement surveys, and how to measure the soil resistivity and the layer resistivity. We can also need to make direct inspection after excavation, and we need to make leak frequency to know the critical zones or positions of the structure. The structure to electrolyte potential is the potential difference between the metallic surface of the structure and the electrolyte that is measured with reference to an electrode in contact with the electrolyte. The measurement must include the magnitude, polarity, units, and the reference electrode. So I can measure the structure to electrolyte potential and say it's 1000. This can't give me any indication. The right thing is to document or write the reading as negative 1000 millivolts according to copper sulfate reference electrode. So I should or must mention these four components: the magnitude, the polarity, units, and the reference electrode. We do this measurement or reading of current of structure to electrolyte potential to locate the anodic areas on non-cathodically protected pipelines, or to determine the effectiveness of cathodic protection system, to locate the stray current, to locate electrical shorts and contacts, like we mentioned in the casing part, or locating coating holidays, like DCPG, minimizing IR drop or the voltage drop. How to minimize the voltage drop? By reduce the distance between the reference electrode and the structure surface as much as we can. Measure the potential with current interrupted, instant of potential. Measure the polarization formation or decay after current on or after left off. We can install external cathodic protection cones to replicate a coating holiday. Here is the method to minimize the electrode contact resistance. We can use wet soil as needed. We can avoid any grass. We can avoid asphalt or concrete or gravel surfaces. We can use access ports like the vote. For pay-by voltage gradient, here is an example. Every line has difference of 10 millivolts per occupational line. If the polarized potential at the structure surface is negative 790 millivolt copper sulfate electrode here, and we measure the voltage and put the reference electrode at the surface here, the meter will not measure the true potential here. There is difference according to the number of the occupational surfaces between this point to this point. Here he assumes that every occupational line have a difference of 10 millivolts, and the difference between this point to this point is 10 lines. So the potential difference is 100 millivolts. So the voltmeter or the meter here will read negative 890 millivolt copper sulfate electrode. We can make current interruption to measure the polarized potential, the instant of potential. If we have multiple sources of current, all sources must be interrupted together. We must read the potential quickly before depolarization happens to the structure. If we have spike like this, we should miss the spike and get the reading after the spike. Okay, this is not the off potential, but this is the off potential. Here is the difference between the on potential, the off potential, and the native potential, or depolarized. If we don't have interrupter and connect the reference electrode to the structure, we can measure the on potential only. If we connect an interrupter, we can measure the off potential here. The difference between the on potential and the off potential is the voltage drop, the IR drop. Then, if we switch off the rectifier, the potential will decrease or go towards the positive direction till it will be constant here. This is the depolarized potential. For new structure, before applying cathodic protection system, we can measure the native or the free corroding or the static potential here. After applying cathodic protection, the potential will become more electronegative to the off potential and the on potential. Our two criteria for cathodic protection are the off potential become negative 850 millivolts according to copper sulfate electrode, or the difference between the off potential and the native potential become 100 millivolts polarization or depolarization or polarization decay. Here is a method to measure an accurate potential by installing or installing the reference electrode at the center of the tank. Here is the difference between the readings taken from outside and the reading taken from the center. It's clear that the center position have less negative potentials, which mean the center of the tank is not protected. The external coupons could be used to represent coating holiday from the same metal. We can use small coupons to avoid excessive current drain on cathodic protection systems. We can bury it at the same depths of the structure. We can put a reference electrode at coupon or in soil tube. We can measure the voltage drop free potentials by disconnecting coupon without the need to install current interrupter. This is the advantage of the code. Current measurement. We have many methods to measure the current, like galvanic current output. We can measure the current from the galvanic current output, or the impered current output, or the current in structure, or the bond current by measuring through the shunt, or using zero resistance ammeter, or by using clamp meter. We also can use the 2-wire line current test or the 4-wire line current test. This is the most common test method, the 4-wire line current test on current span. Another survey is the electrical isolation. We should do this survey to indicate if there is short or metal to metal contact or not. Significant electropositive change in normal structural to potential to indicate decrease in resistance according to short to another structure. Also, to evaluate the discontinuity or the continuity of the structure. Any sudden change in the structural to electrolyte potential along a structure. Measuring the electrolyte resistivity using Wiener-Furman methods, or soil box, or electromagnetic induction methods. Here is the four-wire, the Wiener-Furman methods. We can use this device to measure the resistance or the resistivity of the soil. 4 pins are installed in the soil with distance equal distance, which A. The device will give us reading, which is the R. Then we calculate the resistivity from this equation. Also, in the course of Cathodic Protection Basics, we will discuss the furnace layer resistivities using different distances here. If we change the distance A to different values, we can measure the resistivity of the layers. Layer 1, layer 2, layer 3. We can measure the resistivity of each layer. The resistivity of layer 1, the resistivity of layer 2, and the resistivity of layer 3. 3 current interference is important to know. 3 current is the current through an electrical path other than the intended circuit. Interference is any detectable electrical disturbance on a structure caused by 3 current. 3 current, not galvanic corrosion current between anode and cathode in the same structure. 3 current or interference can be classified being static 3 current or dynamic 3 current, direct current or alternating current. The AC can be both safety hazard and corrosion hazard. 3 current analysis, we should know the source of the 3 current, the area 3 current enters the structure, and the area it leaves the structure, the magnitude of the 3 current, and how can 3 currents be mitigated. In the dynamic 3 current, the current changes in amplitude and direction. The dynamic 3 currents are man-made or geomagnetic, like a telluric current. The sources of dynamic 3 currents may be transit systems, welding jobs, mining operations, electrical power transmission, industrial plants, and the telluric 3 currents. Here is the transit power line, which goes 3 current to this pipeline, which is parallel to this transit system. Here is the current leave its path and picked up by the pipeline through the ears. Then when the pipeline come near the station, the stray current is charged from the surface of the pipeline, causing corrosion here. This is the anodic area, and back to its path. How to mitigate stray current? Stray current from one or more sources. To successfully drain stray current from structure, we should drain this stray current safely from the structure. Structure must tend to discharge stray current at bond. We can install bond. Source must tend to pick up stray current at bond. Interfering structure must be more electronegative than interfered with structure. Sufficient current must be drained. Static stray current, which come from the cathodic protection systems, maintain constant amplitude and constant geographical paths. Here is two pipelines crossing each other. This pipeline is protected by these cathodic protection systems, and these are anodes which protect the structure. The current is intended to be picked up by the yellow lines. This yellow current is the cathodic protection current to this pipeline, but the stray current will be picked up by the other or foreign structure here, and at the crossing, this stray current will be discharged from this structure and come back to its original structure here. The problem occurs in the discharge point here, which corrosion will happen. Types of interference: current discharge interference and current pickup interference. Here is current pickup point, current pickup point, current discharge point here. The current discharge interference, this is a structure, and this is protected structure by these cathodic protection systems. The structure collects the cathodic protection current here. This foreign structure will pick up the cathodic protection current as a stray current from here, and then discharge it from here. This is a discharge point which will be corroded. So the foreign pipeline located in the interference in the cathodic gradient of this pipeline show this is current discharge interference or cathodic interference. Here, this is a pipeline, and this is the anode, and this is the anodic gradient around the anode. The foreign pipeline crosses this anodic gradient, so will pick up current here from this anode. The foreign pipeline will pick up the current from the anode and discharge the current in other direction. So here is a current pickup interference or anodic interference. When we make closed interval potential surveys, points which have positive shift in the potential represent current discharge point, and point which have more negative potential represent current pickup points. How to resolve the problem? We should provide metallic return paths for the interfering current. We may install sacrificial anode by interfering pipe and connect to the interfered with pipe. We may consult the owners and the electrolysis coordinating committee to readjust the source voltage and current. We may remove or relocate the interfering current source if applicable. We also can prevent the pickup or limit the interfering current. We can adjust the current output from the interfering system, which causes interference. We can reduce the stray current as a source. We may apply coating to strategic areas, which is the current pickup, not the discharge areas. Again, we can't apply coating to the discharge point. It will increase the corrosion and make it more severe. But we can apply it to the pickup areas only. We can relocate the structure if we in the construction phase. Also, we can install isolation fittings which will raise or increase the resistance of the structure. Here is a mitigation. This is a drain point or mitigation point for interference. And instead of the current or the impressed current, the interference current, discharged from the pipeline, it will discharge it from this pond, which has the green color. Also, for a transit system, a mitigation pond could be installed between the pipeline and the DC substation, so the stray current will not discharge from the structure to the soil through corrosion reaction, but it will discharge it through the metallic bond. Also, we can install galvanic anode so that the interference current or the stray current will be discharged through the galvanic anode, and the corrosion reaction will occur in the galvanic anode surface, not the structure surface. We can apply coating, as we mentioned, in the pickup areas, not in the discharge areas. The AC interference between the pipeline and the power line, we have three main types of AC interference: the electromagnetic induction coupling, and the electrostatic coupling, and the conductive coupling. The AC interference mitigation, by installed structure removed from power line where practical, we can install surge protection across the isolation feature. Also, we can install grids to above ground pipe for safety hazards. We can install shallow ribbon or grid. Thank you for listening and for your attention. And you can send any questions and we can reply it.
Mr. Hossam, thank you so much for very, very well explained information about this session and your time.
Thank you, Mehdi.
Thank you. Dear participants, if you have any questions, you can write them to the chat box and I will read them for speaker. Also, you can unmute yourself and ask your questions, please. Also, I want to say that we will send the recording to the group, WhatsApp group, after the session as soon as possible. And you can watch it on YouTube. Mr. Hossam, I can see any question at the chat box. The participant says thank you for your time and slides. If you want, we can finish here. Mr. Hossam,
okay, thank you, Mahdi. Thank you, everyone.
Thank you so much. Good evening for everyone.
Okay, goodbye.
Goodbye, goodbye.